Well, hello everyone, and welcome to today's webinar. Thank you for joining us for this first feature of our new Delta Academy series, Building Science Deconstructed. My name is Marcus Jablonka, and I work with Dorken as Vice President of Operations and Marketing. Dorken manufactures a range of high-performance products for the construction industry. Amongst them are drain boards for foundation walls, rain screen materials, air and water resistive barriers, roof underlayments, just to name a few. The company was founded in 1892 in Germany and has its international headquarters there. The North American headquarters are in Canada, just an hour outside of Toronto. We will have a live Q&A session at the end of this webinar. So therefore, we have turned on the Ask a Question feature. You will find a Q&A button in your control bar, likely at the top or bottom of your screen. So if you do have a question, please drop it in there, and we will try and get to it either during the presentation or collectively at the end. And in case you miss anything, please don't be concerned about that. We will be recording today's webinar and we'll make the recording available to everyone. And with that, I would like to introduce today's presenter, Dr. John Straube. He is a principal at RDH Building Science. He's also a professor at the Civil Engineering Department and the School of Architecture at the University of Waterloo. And beyond that, he's a structural engineer, a researcher, forensic expert, an author, often an expert witness, but above all, he is an extraordinary mentor. And therefore, we are very excited that he will be presenting today's webinar, Beyond the Perfect Wall. And so now, without further ado, he is our presenter of the day, John.
Thank you, Marcus. That's a very nice introduction. I appreciate it. Today, I'm going to report from an undisclosed location, a webinar, where we're going to try and have a little bit of fun about going a bit beyond what does the perfect wall always mean. And let's just assume that everybody is safe, or you wouldn't be wasting your time talking about wall design. I've taken my mask off because, of course, the internet is COVID-19 friendly, thank goodness. I suppose I need to start with saying that, hey, we have to put disclaimers in. The normal rules of business apply. And so lawyers are still around despite the COVID-19 pandemic. And so that means that I have to put in a disclaimer that what I'm going to tell you today needs to be managed from a professional perspective, that you have to interpret the information. So what I'm really going to talk about is I want to be presenting about building enclosures, sure, because we're talking about the perfect wall. And I want to do a little bit of review of history. And we thought we'd take the chance to be a little bit more, have a little bit more fun, a little bit more discussion of what does it mean to have a perfect wall, and be more practical about it than just the high level theory or concepts. And I'm going to do that by looking at some exceptions to the perfect wall and look at some niggling details where, although it's a perfect wall, it's how do you actually make it work? Because that, in the end of the day, is what we really mostly care about. And I might have to attack some sacred cows about what people think is the best way to design wall systems or roof systems. So we hopefully can have some conversation about that. You're encouraged to use the chat box to type in some questions, and Marcus is going to try and curate them, and we'll pick some times where we'll be able to go through some of those questions. And the commentary here is also, although I'm going to talk about both wood frame and non-combustible, a lot of the examples are kind of mixed climates and so on. So it could be, you know, really cold climates. It could be middle cold climates, like, say, what would that be, Tennessee? I know that we have people from all over, and I'm not specifically talking about hot, humid climates, but I'm hoping that some of this will come up. Now, some of the reasons that we're seeing more and more discussion about the perfect wall, or even just how to design enclosures in general, is because we're being asked to deliver at a higher level. And the higher level is really about carbon and energy and etc. So we have health, we have code, we have resilience, and so on. So that's where the context of this comes from. I'm going to see if I can adjust the share to be maybe a little bit more like this. So maybe you get you don't get to see the preview of what's coming up next. You'll only get to see what's happening. So what has changed in the last, let's say, 100 years is that we've moved from a single layer are made of a few materials, such as the solid masonry wall that you're seeing here on the left-hand side, to hollow systems that are much lighter weight and layered of many different materials. And we've done that because we're trying to achieve higher performance, faster construction, lower cost, less embodied resources, etc. There's a whole bunch of competing trends as to why we end up that way. And actually, for most high performance systems, we are going to end up with a hollow, layered, many materials type of approach. However, as we've moved from that solid sort of masonry, adobe, log cabin, to the multi-layer wood frame, steel framed with insulation and membranes, it is possible with all of those options to completely screw things up. And so we have more opportunities to make bigger mistakes. So that's why we really need to understand and roll back and think about more what those changes have meant. So as we've moved to these other changes, we have added layers. And one of the challenges is that you end up not seeing, you're not labeling in construction documents or on the construction sites what things are doing. We're just labeling what the materials are. And that causes a tremendous amount of confusion. And like the masonry veneer that replaced the solid masonry is a real challenge because we don't know what it's for, or many people don't know what it's for. Maybe people here know what it's for, but some people on a job site would actually think that the masonry veneer stops rainwater, which of course is laughable if you've ever sprayed water on a brick veneer. And similarly, we'll talk about things like house wrap without actually explaining, well, what's the house wrap for? And therefore, we get lots of confusion because there are lots of options available. And so the drawing on the right is not an inaccurate drawing, but it doesn't tell us what anything does. So with these more changes and this more complexity has created all of these challenges, and therefore we need to get greater clarity and simplicity. And that's where across the horizon comes riding the knight on his white horse saying, oh, the perfect wall will answer it. And the good news is that there's a lot of advantages to looking at this perfect wall. And for many of you, this is going to be a review, and that's why this presentation is beyond the perfect wall. It is a review. So the dashed red line there shows where are the guts of the hygrothermal performance of the enclosure. There are the layers called the water control layer, number 1, to avoid rain penetration problems. Air control layers, number 2, to prevent condensation issues and air quality issues inside the building. Then we have the thermal control layer, which provides comfort, condensation control, and code compliance. And then we have the vapor control layer. So it's knowing that we have these 4 layers in almost any functional building enclosure, and we have more. Sometimes we have to add fire control. Sometimes we have to add sound control, depending on the kind of building occupancy. And then we have our exterior finish and our interior finish. And this is, quote unquote, the perfect wall. I always put quotes around it because it actually isn't the perfect wall for most people's projects. Or we have lots of competing interests why we might do something different. So the reason we describe this as a perfect wall is that, well, it has a real clear function. That's one of its biggest benefits, is that it tells us this layer is for water, this layer is for air, this layer is for thermal. And that cuts through the confusion in drawings and specifications, job site instructions, etc., about why we're doing what and how we should do it to get to our outcomes. Another thing is, this is an ideal arrangement. So by ideal, I mean the normal materials that we use for water and air control would be protected by putting them on the inside of the insulation so that it doesn't see temperature extremes. It sees constant indoor conditions. And so that's one of the reasons for this arrangement. Another reason for this arrangement is it works really well if you have a humid inside and a cold outside. Some people are, let's say, from Texas, and there are places like, say, Austin, where in the wintertime, we need to worry about preventing humid air from indoors leaking out and condensing on the outdoor side of the wall system, causing damage. Well, this arrangement is perfect for that. However, it also gets hot and humid occasionally, a little bit hot, a little bit humid, in places like Austin, Texas. And now we have to ask, how does this handle that moving inward? Well, it turns out that it actually does a fine job in Houston or Charleston, South Carolina, etc., Kansas City, Missouri, when it's really hot and humid out, because any condensation that might happen is going to occur on the left side of this drawing, meaning on the water control layer. And condensation on the water control layer is okay because it's a water control layer. So one of the most common questions is that, well, why shouldn't the water control layer be on the outside of the insulation? No. The reason that that's not usually the perfect location, and the reason the perfect wall never includes it there, is that it exposes that water control layer to the hottest temperatures when the sun shines on it. So it gets up to 150 degrees in the summertime, sometimes 170 degrees Fahrenheit, which is like 60 degrees Celsius. And in the wintertime, it drops it down to the coldest temperature you have in your area, which, depending where you are in the world, it could be 20 degrees below Fahrenheit or 40. And that exposes that water control layer to huge temperature variations, and that's a stress. Another reason is that that puts the water control layer at full exposure to all of the water, and it doesn't take advantage of the insulation to protect it. We're going to get into that a little bit. So from a building physics perspective, knowing the material properties we have, this is the best arrangement. But let's actually...
John,
yeah.
Sorry for interrupting, but there's two good questions here, if I can throw them in very briefly. So one is, how would the insulation then have proper protection from absorbing water through a veneer?
Yeah, so the whole basis of this is that the insulation we're using are things like polyisocyanurate, extruded polystyrene, expanded polystyrene, or stone wool. Those are the 4 most common uses of types of insulations that's used in a continuous exterior insulation way. And that means that all of those materials can tolerate wetting by design. Those products, now, I can't use cellulose. I can't use batt insulation, which is not self-supporting, because it'll collapse. But the products that are used in this exterior insulation, which is built into the perfect wall concept, are all entirely designed to manage the amount of water that gets there. But part of the reason that this perfect wall isn't applicable everywhere is what I'm going to talk about, is that, well, there are times when you can overwhelm that material capacity for applications. Not these simple, straightforward walls that we're seeing here. In fact, the concept about why do we have the water control layer on the insulation, not behind it, as I've shown it. Well, actually, in the past, and many people don't realize this, in the past, we didn't even have a water control layer. So these are images from a couple of sources, influential sources in the 70s and 80s, about how we came to the idea of the perfect wall. And notice that they don't include a water resistive barrier. And in fact, this is still something you'll see a lot of in European literature, where they don't include a water resistive barrier over top of the support structure because they hadn't realized that it was important to protect the masonry or the wood from water. So these are the kinds of reasons why today we've ended up at a water control layer here behind the insulation, but over the supporting structure, even though the historical development took a long time to get to that point. So people don't realize often that it took us well into the 90s to recognize that a water resistive barrier was needed. And in fact, the term water resistive barrier only started in 1997 in the US building codes. And we still don't have it in the Canadian codes, but we do have a term called a second line of defense, which is the code requirement for another water resistive layer other than the cladding. So in the past, we actually had a lot of focus on things like pressure equalization, not on WRBs. And today, and we'll talk a bit more about the arrangement. Okay, today we should at least make sure that there's 3 distinct, labeled, and in the specifications items. The water control layer, which is often we call it WRB, the air control layer, and a continuous insulation. Now, many times we combine that water and air control layer into one product, but we don't have to, and I'll show you examples where we do not. Also, that water control layer doesn't always come out of a pail or off a roll. Sometimes it's part of the assembly. So for example, in glazing systems, the glass is the water control layer. Or in precast concrete, it's the precast concrete that's the water control layer. If we're talking about wood and steel light framed assemblies, yeah, we almost always are going to get a off a roll or out of a pail WRB. And in those cases, we're almost always combining the performance of air barrier with water control. But you need to be clear about it because there are many options to separate water and air, and unless it's labeled, it's not, confusion can reign. The reason I put ish behind continuous insulation is that, well, it's not always really continuous. In fact, there's a lot of debate about how continuous does it have to be. So when we attach cladding to the support structure and the enclosure, we actually penetrate the insulation layer. And that's one of the issues with, is it continuous insulation? How big of a connection is allowed? And there are many jurisdictions in Canada and the United States where they will ignore things like balconies penetrating through or floor slabs, both massive penetrations of the thermal control layer, but they're sort of just say, yeah, okay, it's hard, I give up. But on the other hand, there are jurisdictions where they're saying that's not good enough. You need to develop technology and designs that make that insulation closer to continuous. We're going to explore some of the rain screen questions in a moment, but one of the reasons that this perfect wall is perhaps less than perfect as shown on the drawing is that we have to attach that exterior finish, that exterior cladding, back to the support structure. And that results in a whole bunch of design issues that are needed to be managed in the modern world. Does it make the best use of materials? By putting all the insulation on the outside, as was already discussed, is that, well, I'm limiting you to a certain kind of material, semi-rigid, continuous insulation of extruded, expanded, polyiso, spray foam, and rock wool. But what about if I want to put insulation inside the support structure? There's really economic, environmental reasons to do so, and we'll even find out there may be some performance reasons to do so when we dig into this a bit more. So obviously, in the recent past, we've been building wood-framed and often even steel-framed assemblies that look something like this. We have the water control layer on the outside, and the air control layer might be on the inside, might be on the outside. One of the reasons that people think that the water control layer has to go outside of the insulation is that they're thinking about wall assemblies that we've built like this. And the reason the water control layer is there is that, well, we have to protect the structure, the wood frame structure, from moisture. It's the thing that needs the protection. And we're using low density insulation in the stud cavity or cellulose or other products that are susceptible to moisture, so the water control has to be out there. But that's only to accommodate the limitations of those materials, not that that's the best place to put it from a building science perspective. Another question that arises is, well, should the air barrier be out there, or should the air barrier be on the inside? Well, again, because this isn't the perfect wall, there's a lot of confusion about how we would do that. The air barrier can be on the outside or the inside, but the building physics would say, no, 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 you've got the insulation in the wrong spot, so don't even talk to me about locating the air or water barrier. So as we've moved towards the perfect wall concept, driven by performance, demands of a better insulation and better airtightness, we have tended to move to the wall on the left-hand side. But the transition has often looked like the wall on the right-hand side. Builders, designers have simply said, I need more insulation, I'll just slide it in between the water control layer and the existing wood or steel structure. They didn't change the location of their air barrier to now putting it on the exterior of the structure, which means that, which means that today, as we do these hybrid walls, the ideal location for the air barrier is to be able to put it on the outside of the wood sheathing, but on the inside of that continuous insulation. Now, one of the examples of a common wall system that is not exactly like the perfect wall, but is darn close, is drained EIFS, exterior insulation finish systems, synthetic stucco, sometimes people call it. In the old days, this was made with no drainage gap at all and no water control layer in behind the insulation. And that lamina finish was actually the water control and the air control as well, even though there was nothing behind it. The moment we go to a drained EIFS, it actually gets really close to the perfect wall because we have an air and water control layer that's continuous over the entire sheathing and frame structure behind. We have a drainage gap. We have continuous insulation, which in most cases has no fasteners through it at all. So it really is continuous. And so, hey, we went from a system that had a lot of problems, especially on wood frame, to a system that's a very close example of a perfect wall that's affordable and buildable. But remember, that key thing was making sure that we had a protected water control layer and a continuous air control layer. Another example of a successful wall system that steps away, in this case, a much bigger step away from the perfect wall concept or ideal, is that we have the sandwich panel sandwich panel precast concrete. So in this case, we have two layers of reinforced concrete. The outer layer tends to be thinner, inner layer thicker. And there's a continuous layer of thermal insulation. So that's not a continuous layer, actually. There are connections between the two, which are often made today of either stainless steel wires or carbon fiber and glass fiber composite ties to really result in very low thermal bridging, and so very close to continuous insulation. But here's the big difference, is that we actually have a water control layer in the form of the exterior concrete, which is quite different in that it's exposed to the outdoors. So why is that okay in this case? Well, the reason it's okay is that it's made of 2.5 inches of precast concrete. It's not made of paper run through an asphalt bath. So this is a very durable material built in a factory at scale with essentially no holes in it, because you don't have to put nail fasteners through or anything like that. And therefore, this exposed exterior location of the water control layer actually performs very well, even though it is not the perfect wall. The air barrier does tend to remain on the inside in the form of that 3, 4, 5, 6 inches of precast concrete. That is, again, though, factory built and continuous. And of course, that means that all the action is at the joints. And so that's where we have to have 2-stage joints and so on and so forth. Not going to get into that, just going to say this is not the perfect wall, but it is a perfectly durable and high performance wall when it's designed even with a modicum of competence. This is another building enclosure assembly that we see on all kinds of institutional and commercial buildings. It covers what my guess would be 1/3 of the entire enclosure area of North American commercial institutional buildings. It is the exposed membrane low slope roof. So this is a membrane put on the outside, which is the water control layer. And then we actually have the thermal control layer, which is pretty continuous, although the number of screws going through it can add up to being measurable. And then we should have an air barrier and probably a vapor barrier at the deck level. And that's not the perfect wall. There's not a drainage gap. The water barrier is exposed to the outside. And even so, this is a practical system that is lighter weight than the perfect roof solution, which I'll show you shortly. It can and does work quite well, but that fully exposed membrane, depending on what membrane you install and how you maintain and do it, you might only get 20 years, 15 years, 20 years, or you could get 30 or 35 years. So that is a limit to this that most people find a reasonable compromise. The perfect, quote unquote, roof membrane would look like this. It would look like a support structure, an air, water, and vapor control layer, insulation, and then some ballast to stop the insulation from blowing off. The insulation here is actually completely continuous, no thermal bridging. However, we've learned that you need to provide at least a small amount of drainage between the insulation and the air-water barrier membrane, which is the roof membrane. And so that's a change from the perfect wall. And also, we've discovered that there's a lot of water gets down to that membrane, and that is more important to thermal bridging than screw fasteners. That can be a 5 or 10% hit on your annual thermal performance. And so improving that means that we're starting to move a rain shedding layer on top of the insulation, which again is deviating from the perfect wall to accommodate materials and reality in the real world.
Ron, a quick question in between.
Mm-hmm.
Someone is asking here, what is your opinion of an ICF wall with respect to the other wall system you showed?
Interesting. I had not, I don't have time to look at each of these, like SIPs are another exception, structural insulated panel systems, ICF, insulated concrete forms, also an exception. So with ICFs, they actually often will require you to put the water control layer on the outside of all of the insulation. And the underlying support structure and insulation, incredibly durable and strong, but it does mean that your water control layer is put on the outside of that. And that means it's exposed to more temperature variations, and so it's not as the ideal wall in terms of perfect wall. Is that a problem? Well, if you're choosing a durable water control layer, no, not a problem at all. But you do now need to think about how you're going to get a vapor permeable water control layer. Now you have to consider that you can't just put up any water control layer. It has to also be vapor permeable because it's outside of the insulation. And in most climates above zone 3, you now need to make sure it's vapor permeable, even sometimes zone 2. I'd mentioned cladding attachment as a limitation is that, I'm showing you some images from RDH's thermal bridging guide for cladding attachments. And there's a lot of ways you can minimize thermal bridging through the insulation. However, all of them tend to involve screws. At the end of the day, we're attaching something back to the wood or steel frame structure with screws. And those screws are small thermal bridges and potential penetration sources for water. The good news is that this is not a big problem for most assemblies most of the time. The thing to know, though, is that sometimes it can matter, and you have to be able to distinguish between when does the screw matter and when doesn't it. So let me give you some example. So on the right-hand side, we have an example where there is a screw that's attaching cladding onto a building through, in this case, the picture on the right is about 6 inches of stone wool insulation, and there's a water droplet there. Now that water droplet is because of condensation. You might believe it's due to water leakage, but in this case it's due to condensation, and which is much more common because it's a cold climate and it's cold outside, and on the inside of this building it's actually very humid enough that my glasses would fog up with moisture when I walked from outdoors to indoors. And so the exposed screws were fully open to the indoors. It was a high humidity environment, and so you get condensation. This can be a problem. On the bottom left, I have an example from the Alaska Housing Research Center, the Cold Climate Research Center, where they did a manual on how to insulate on the outside a la the perfect wall. They call it a remote wall. There's an acronym there, but it's the perfect wall. And when they have the screws penetrating through, they're saying, oh, we need to insulate those screws because you can get condensation as shown on the right. Now that's true in really cold climates, zone 6, 7, 8. It's also true, more importantly, that when you have high interior humidities, not shopping malls and condominiums, but swimming pools would be, or hot yoga studios, then you'd have to worry about this stuff. This is showing some commercial systems. This one on the is showing a metal panel system, and the screw attachments, I'm trying to zoom in there and show it to you. The blue is highlighting. Those could be cold because they penetrate from the outdoors to the indoors. But 2 things have been done in this design to avoid condensation. One is they spaced it in 2 steps. So first, the only screw from the outside goes into a hat channel, and then the hat channel is screwed into the stud. And secondly, and this is a common one, they covered it up with spray foam. And so here's a reason why you might actually want to put insulation in the stud cavity, inboard of the air barrier and the water barrier, because you want to insulate those screws coming through in a high humidity environment. Most of the time, when that's a concern, one does use spray foam because it's both air and vapor resistant. Most of the time, we don't need to. Most of the time, we don't have a combination of cold enough outside and humid enough inside that we have to do anything. Now, adding some resistance on the inside is always useful, and normally we do that by just putting the bad insulation in that space and drywall without any big holes. And that actually is enough to stop condensation on those screw heads for normal type building occupancies. Which brings me to, well, are there other reasons I might put insulation into the stud cavity? Well, for sure there are. If you're building with wood framing, the benefits of insulating between the studs are very significant, meaning that if you purchase an R20 batt insulation or R20 of cellulose blown in insulation, you get around 70% of that R value despite thermal bridging through the wood studs. If you're doing steel studs, well, then you're losing about 3/4 of the thermal performance. So there's less argument to put insulation into a steel stud, but there's a strong argument to put it into a wood stud. And that means that we end up having assemblies that are not the perfect wall, as you can see on the right-hand side section, but a layer of insulation on the outside of the air and water barrier and a layer of insulation on the inside between the wood framing. This overall assembly has modest impacts from thermal bridging. They're still there, but they're quite manageable. And also manages things like screw attachments, thermal bridging, and condensation, reduces the overall wall cost per R value, and reduces the wall thickness per R value. And all of that means that this is a preferred design, even though it's not the perfect wall. And we see a lot of this wall, and it also means that you need a vapor permeable water resistive barrier, air barrier. And so we need to make sure that we're choosing a slightly different membrane versus the perfect wall where that membrane could be a vapor barrier. And this allows for the best in terms of thermal, etc. I just noticed a comment coming through that ASHRAE recommends 30 to 50% humidity for all building interiors in cold climates. And 30% relative humidity inside won't cause condensation in a cold climate building. 50% completely will. But then that's why that recommendation has to be interpreted very carefully. It's something we deal with all the time. The difference between a 30% relative humidity interior when it is below freezing outside and a 50% interior is dramatic and vast. And that means that you can't use that wide of a range in a cold climate building. If you're building normal wall assemblies with normal windows and normal window attachment details, 50% in a climate zone 6 or 7 is insane. It's a special building. It's closer to a swimming pool. 30% completely normal. And by the time you get to zone 8, even 30% would be seen as a special use building. And so those ASHRAE studies have to be very careful. What's even worse is to hear medical doctors weigh in with what the relative humidity should be in a building. And I have done more than a few forensic legal cases when somebody followed a medical doctor's advice when it came to the design and operation of their buildings, and as a consequence ended up in the hospital because their entire building turned into a mold factory. And this has happened more than once. So I'm going to stop recommending to you what kind of medicine you should use to treat COVID-19, and I think medical practitioners have to back away from saying things about how we manage our buildings, would kind of make a lot of sense. So this air and water layer, this hybrid or split system is one label that's used, more on the West Coast, I think. But what's key is that it maintains the benefit of the perfect wall of wrapping the air and water barrier outside the primary structure. And the benefit of that is a number of things. One is it does minimize condensation issues and risks. Secondly, it improves the water resistance in a way I'll show you shortly. And most important of all, it manages the number of penetrations and details that we have to manage in our attempt to get the air and water control as continuous as possible. We can't tolerate holes, very many holes in the air layer, and we can tolerate very few holes in the water control layer. And the best way to manage that is to make sure that we have simple surfaces over which to apply them. Attempting to put the air barrier on the inside of a wood framed or steel framed structure, wrap around the rim joist or the steel beams, depending on the type of building, is massively complicated. It's possible, complicated. By wrapping it over the outside, and in the photograph you see here, you may not notice without at first glance, it's an extreme approach because actually all of the overhangs and detailing around normal buildings are, in this case, were added on afterwards. They're tacking them on so that we can wrap that membrane literally from the roof over onto the wall and minimize all of the details. and then we add overhangs later on.
John, there's a quick question here where somebody's asking, it's hard for me to imagine an air barrier which is vapor permeable. Do you have a way to think about what material that would be?
Yeah, sure. I mean, actually, I would suggest that, Marcus, you should be telling people all about the wonderful products you provide that are both air barriers, water barriers, and vapor open. But I can give you some other examples. Gore-Tex. In fact, in the outdoor apparel business, we've been making airtight vapor permeable layers forever. And there are lots of materials, and the way we do this, the magic that chemists and manufacturers do, is that they make the holes small enough between the different fibers that make up a fabric that the fibers, the openings are large enough for the tiny water vapor molecule to get through, but the gaps are still small so that they stop the much larger oxygen and nitrogen molecules getting through. And so there are many materials, for example, craft paper. It stops air and it allows water vapor through. Now, the problem with craft paper is that it might not be strong enough to resist wind loads, and it isn't water resistant enough to be a water barrier, which is why most of the materials we see in practice are polymer-based products, so that they can be water resistant and vapor permeable. And then to make them strong enough, we often used human-made polymers as opposed to relying on wood-based polymers coated with asphalt. But there are many, many products that are vapor permeable and airtight. Oh, by the way, so now I want to talk a little bit about rain screen. Many times I see it conflated. A rain screen wall is a perfect wall, and that shouldn't be done. Rain screen, I put quotes around it because I don't know what it means. There are three variations here of what a rain screen wall could look like. You have the drained wall system, which is a rain control strategy. And that doesn't need to, that is what's employed in the perfect wall, but you don't have to use it all the time. We have the drained and vented system, and then we have the drained and ventilated system. So each of these systems is described by some people as rain screen and other people as not. All I know is a rain control strategy, drainage is the fact that this is a differentiator. So you need a water control layer, flashings, weep holes, and a gap. So many rain screens were built that are not the perfect wall. As an example, on this drawing, I'm showing that all the insulation is between the framing. This could be a steel framed wall with the membrane on the outside. From a drainage point of view, it absolutely is a good water control system. As a thermal solution, it's horrible. And that's why we've moved to having to put CI. But even on wood frame walls, it's not a horrible thermal wall, but it's got limited performance. You really need to put exterior insulation on to get continuous and to move towards the perfect wall thermally. So don't confuse the rain screen concept with perfect wall. Drainage or rain screen is one strategy, and it is used by the perfect wall for rain control. But there's other things about the perfect wall. And in fact, there's a real challenge about simplifying the rain control too much. So many times we have moved towards, we need a WRB, it needs to be installed perfectly with no holes. Definitely good advice. On the other hand, there's a difference between a roof membrane and a WRB for a reason. A roof membrane sees all of the rainwater. A WRB is used in a multi-layered assembly where each of those layers reduces the amount of water that penetrates, so that a WRB sees much less water than it would in an exposed system. So I'm showing here sort of 5 steps, really 6, because the first step is, well, how much water are you getting? Are you in Florida in a hurricane, or are you in northern Omaha in a drought. Do you have a 20-story building or a 1-story building? Are you surrounded by trees or the ocean? So all of those things really change how much water gets onto the wall in the first place. Then the question is, how leaky is your cladding? So we see a wide range of cladding systems. And for example, brick veneer lets a lot of water through. So does vinyl. But EIFS doesn't let much through at all. Then we have how drained is your ventilation gap. And I'm showing a ventilation gap there. You could have drainage off the back of your cladding, and how water repellent is your insulation. Is your insulation intended to shed water or not? And then finally, we have how drained is your drainage gap. So there's a gap there that water can run down and out. And then finally, we get to your water resistive barrier, your water control layer. And that, by knowing what 0 through 4 are, you can have a much better idea about what kind of a WRB you need for 5. It can lead people to bad decision making in design to think that it's all about the WRB. That is a perfect barrier solution if it's all about the WRB. Whereas a rain screen solution and drain systems are multi-layered and rely on many other components of the system. So this comes up fairly often in tilted walls. In some architecture, especially architecture with large budgets, we see walls that aren't vertical. And that changes everything, because now if I look on the left-hand side, if I have a open jointed cladding or just a mere leaky cladding, as soon as it's on an angle, a huge amount of that water that falls on that assembly can now get into the space, and it will be driven by gravity across the cavity, onto the insulation, through the joints in the insulation, and a lot of it will end up on the WRB. And so now I have a whole bunch of water on the WRB that under normal circumstances I wouldn't. So one of the things we do about that is shown on the right-hand side. These types of assemblies have been built for a long time, and they don't usually rely on a single membrane because it would require a very good membrane, closer to a roof. And what we see here on the right-hand side sketch is another layer, a water shedding layer outside of the insulation. And this goes to now allow me to protect the insulation, not from all the water, because the primary water barrier is still going to be back at the sheathing, but it means that I can shed a lot of the rainwater off, and now the WRB is seeing a moisture condition more normal of a wall for which it was designed. So this is an example of the botanical gardens in Denver, a very interesting project. You'll notice that those look more like walls and roofs. I'm not sure which they are, but they also have open joints. Those are Swiss burl panels with open joints. So when the rain falls on this building, it's 100% going through that cladding. That's not just a pattern. Those are actually open joints. So again, using this concept of an outside layer that sheds rainwater and then an inside layer that is your primary air and water barrier, you can use normal materials, but you're adding that additional rain shedding layer so that the materials that are normally used in construction can be used for a tilted wall. If I tilt it further, I might call it a roof. And in a roof system, in a cold climate, this would be sort of the closest to the pitched perfect roof. In fact, this roof, as shown here, this assembly would probably be better than any low slope roof. It would be safer in a high interior humidity environment. So you'll notice where we again have a water control layer outside of all of the insulation. Is that the perfect roof? No. But for this application, it is perfect because it allows me to have a vented space over top of it. It allows me to have wood sheathing, which needs to be protected from water, but also is much better in terms of thermal performance when I'm putting screws through it, etc., to get to a system where I solve all of my problems: water, condensation, and available materials, trades, and budget. So that's why there are quite a few this is an ideal solution for a pitched, modest span swimming pool in cold climates, and it's not the perfect roof. And also, we often end up with, again, where the wall starts and the roof starts is pretty unclear here. And this is a cladding system that is usually beyond most of our budgets. But if you have it, you got to do something about making it work. And so there are products that are literally made exactly for this system to ensure that these types of metal claddings, they don't have to be fancy metal or segmented like this, has a drainage gap. And these drainage gap making membranes are moving the water control outside of the insulation because of the higher expected rain load, because it's not a vertical wall. And so there are products that actually integrate the gap making, it's like a Brillo pad, and they integrate that with an air and water barrier, but the air and water barrier is vapor permeable so that you can use it and not trap moisture in the assembly that's below. So another example of how the rules change when we move to different systems is open jointed claddings. Many of the claddings that we would normally use have at least attempt to close all of the openings. And this means that they manage ultraviolet radiation and they manage rain quite well. When you open those joints, now it changes things. And the also allow UV penetration. And for both reasons, you may want to, again, we can example at Collaborative Life Sciences building in Portland, where they didn't have open joints per se, but they had perforated cladding, something we see into metal, etc. Well, now that's the job that the cladding normally would with a membrane, but now the membrane has to be UV stable. And so that's why they're often black. They don't have to be, but it's hard to necessarily have to be airtight, but it does have to be watertight. And normally the and I want to get ending here with so I'm hoping you can see this. I seem to have had a hiccup.
It's not working again, John. Thank you.
Okay. Cool. So last couple of points here before we wrap up and take some questions and some comments from Marcus. Remember, when I'm talking about the vapor permeance of air barriers, water barriers, that is the right thing to ask and think about. However, other layers in your assembly also have vapor permeance problems or not problems. So you have to keep that in mind, even though we do concern ourselves a lot with the vapor permeance of some air-water barriers, membranes. Remember, OSB has a vapor resistance, plywood has a vapor resistance, metal panels have a really low vapor permeance. So we have to keep that in mind. And at the end of the day, we really also need to solve these things at details. Although we spend a lot of time talking about the layers that we would use in a roof or a wall or a pitched roof wall woof, a lot of the real problems come at transitions, at three-dimensional variations. And so we need to have detailing, and this is where that concept of labeling the air, the water, the vapor, the thermal is so critical, because it's when we're switching between different systems and materials, it's having that clarity of function allows us to detail what things need to be connected to what. And to that end, when we're thinking about air barriers particularly, we need to connect those dots together in a way that's airtight. From we're talking water control, it's okay often to lap them, preferred to seal them, okay to lap them. But from an air barrier point of view, you have to seal them. It's not enough to lap them. And so making sure that we not just think about the materials and layers, but also how we connect those joints all together is a pretty critical factor. And so this is where, you know, the perfect wall is the one we can afford, that the people can build, that manufacturers can supply materials for. And so that's why we often have to make changes from the concept, the simple, useful concept of the perfect wall, and adapt it for what is needed to get this project you're working on the best particular wall / roof. So I'm gonna just turn over to Marcus right now. I've tried to answer some questions during the session, but I don't know if you have anything else that you, so Marcus, you want to jump in there, start sharing the screen.
Thank you, John. Yes, there are, thank you for your presentation, first of all. And there are a whole number of questions. I'm not sure if you will have the time to go through all of them, but I'll try to summarize some that are duplicates. Here's one. Looking at the drained and ventilated wall, how would you address an open rain screen exterior surface? How would you protect the exterior insulation from UV rays?
Right. So that's more what I talk. You meant call it open rain screen. I'm talking about, I call it open. And the reason I distinguish between the two is that an open rain screen can have baffled joints, meaning the joints are open to air and water, but behind the joint is often a piece of metal in a shape of a U or something like that, which intercepts direct rain penetration and direct UV. And in those types of systems, baffled joints, open rain screens, there is nothing to do. When we have the open joint, we have to protect against UV. There's two approaches at least. And the one approach is if you're using a UV sensitive insulation, any of the foam products, then you can cover them up with a membrane that is UV resistant. So that's where there are the membranes I talked about that were usually black in color. And so these are polymers that have a lot of UV stabilization and antioxidation packages put into the polymer that provide you the 100-year lifespan or whatever is needed in that application. Another approach is to use UV tolerant insulation, like stone wool would be. Another approach is to try and cover that up with like something like metal, etc. But that usually is not economical. It's usually better to go to a baffled joint.
Thank you, John. Here's another one. What about double stud walls where the continuous part of the insulation is between the studs? The insulation can be really cheap cellulose.
Right. So again, you're right. I didn't look at the double stud wall. The insulation that you're describing usually isn't continuous because actually we routinely see it penetrated at floors. And there's lots of floors in buildings. And so that's one issue, is that oftentimes that simple two-dimensional section of the double stud wall doesn't show how many thermal bridges actually exist. So that's one issue. And cellulose is it's cheap depending where you are. So that's another thing to keep in mind. However, the big limitation on double stud walls, especially if you insulate them only with cellulose, is the risk to the exterior sheathing when it's made of plywood or OSB, because that is kept cold in cold weather, and that means that condensation that by even really modest leaks can accumulate there. So we have enough, more than 30 years of experience with double stud walls to know that it's not like an overt disaster, but we also know it's a higher risk wall. It's a big step away from the perfect wall in terms of increasing the risk of that exterior sheathing. But if you do a good job of airtightness, if you make sure that you have a very vapor permeable sheathing, it's better to actually go from OSB to plywood, plywood to fiberboard, and even better from fiberboard to exterior gypsum. A highly vapor permeable air water barrier on the outside and ventilated cladding, that's a fairly low risk system. But that's why we didn't mention it much. It's another one of those many walls that are not perfect. But this one, we published a fair bit of measured field results on this. It definitely is a riskier wall than putting the insulation on the outside and the membrane on the sheathing.
Thank you, John. Thanks for answering the questions. Thanks for your presentation. This was great. We have many more questions, but are running out of time now to address them all. So we'll try and do that afterwards in the follow-up. Many of the concepts that John has been talking about today, we take those to develop products that provide solutions for these problems and help for buildings to perform better, to simplify the installation. An example out of that or for that would be a product that we sell under the brand name Delta Vent SA. It's a self-adhering air barrier, so it's airtight, it's watertight, it adheres to the substrate, and we put a self-adhering edge to it to help with the sealing in the overlap area, so one can eliminate any need for taping. And at the same time, that type of product is highly vapor permeable with 50 perms industry leading, and that helps to improve the performance of the building. Products like that are used in high performance buildings. They can be as complex as the one that John mentioned. It can also be a standard building, but in any case, those details help to improve the performance of the building. If you have any need for help with your design with regards to, for instance, a health product declaration, we have HPDs available for our product. We can also help with passive house details. We have them certified by the Passive House Institute, by FIAS US, as well as by Passive House Institute. And we're working with both with the American and the German leg of Passive House. And if you do work with Revit, we also have BIM objects available. So at any time we can help out with that as well. That being said, please feel welcome to find out more about us and our products at dorken.com. And also feel free to reach out to any one of us. We will be sending a follow-up email with a link of the recording for today's webinar. And just as an announcement already, in 2 weeks from now, we will have another webinar with John Straube. It's going to be Friday, May 1st at 1 p.m. Eastern Time. And the topic is foundations and how to keep our bottoms dry. And another teaser, there will be more video contributions by other building science experts. Dr. Joe Stiebrick on open joint claddings coming out soon. Justin Wilson on rain screen technology. And you will find those in LinkedIn, on our YouTube channel, or on Instagram. And with that, I would like to say thank you for joining us today for our first Building Science Deconstructed webinar. It was great to have you with us, and we look forward to seeing you next time. And until then, please be safe. Bye-bye.
Bye.